Hello everybody. In this video we will discuss oxidation of alcohol. So this step is critical in terms of biochemistry because what molecule is this one? This is ethanol. So when we drink ethanol in our body metabolizes it, right? So it's oxidized ethanol to different compounds. So let's see what happened. So this is a primary alcohol. Why primary alcohol? Well, you can figure that out by looking at the carbon atom that is connected to oxygens. So in this case, this carbon atom is connected to another carbon atom, only one carbon atom. So this is why it's primary alcohol. So this carbon atom here is alpha carbon atoms for OH. So this is critical. First thing that you want to solve when you are doing any problem related to oxidation of alcohol, look at the carbon atom that is connected to oxygens, okay? And then look at how many hydrogen it has. So the carbon atom here has, so this carbon atom here, so carbon has 2 hydrogens. Now, if it has 2 hydrogens, that means it can perform, it can. That does not mean it will, that will vary based on the reagents, but always remember, it can perform two-step oxidations. I will explain in a second. Two-step oxidations. If the reagent is available. Okay, so let's look at what do I mean by that. So the first step oxidations, when you oxidize it, is, keep an eye here. So now you see here the carbon atom. Okay, so you noticed the carbon atom, one of the hydrogen is gone, and the number of CO bond increases. So how many CO bond we had here in this carbon atom? So here we had one CO bond. So we see one CO bond right there. And how many CO bond we have here? So you see 1 and 2. So we got double bond, right? So this one has 2 CO bond. So the number of CO bond increases and number of CH bond decreases. So basically it's what you're doing is you're adding oxygens and removing hydrogen. That's the definition of oxidation reactions, right? So when you add oxygens, that's oxidations. So in this, what did we make? We made an aldehyde. Okay, now shift your attentions to here. So this, the same pink carbon atom still has one more hydrogen left. That means it can do one more step of oxidations. So now it can perform this. So this is the natural oxidation pathway. That's pretty much what happened inside our body. Is this is a carboxylic acid. So when we drink alcohol, our body metabolizes it to all the way to carboxylic acids. So now let's try to look at the same pink carbon atoms. Question number 1. How many CO bond this one has? This one has 1, 2, 3. So it has 3 CO bond. So you notice number of CO bond increases again. So number of CO bond went from 1, 2 to 3. And how many hydrogen it has? Number of CH, it has 2, 1. It doesn't have any more CH anymore. There is no hydrogen connected directly to this carbon atom. So you notice the 3 patterns is happening. Number of CO bond increases during oxidation process. Number of CH bond decreases. Hence, it is really critical you should draw out all the hydrogen and figure out how many steps of oxidation it will happen. Forget the reagent for now, okay? Forget the reagent. These are the key ideas. Look at this, how many hydrogen attached to the carbon atom, and tell how many oxidations can happen. And then we'll go over the reagents later. So let's give another problems right here. Okay, so what kind of alcohol is this one? So this one is, you always look at the carbon atom connected to the oxygens. So this one is a secondary alcohol. Okay, so this one is a secondary alcohol. Now next questions, how many hydrogen it is connected to? It is connected to only one hydrogen. That's important. So it is connected to one hydrogens. So which means how many step oxidation it can do? It can only perform one step oxidations, no matter what the reagent is. Okay, so don't worry about the reagent for now. We are focusing on the key idea. So let's say you oxidize this. So when you oxidize it, what would you be making? CH3. Okay, this looks ugly, but that's okay. So right here, not green. Okay, look at the pink carbon atom. Okay, so the pink carbon atom has how many hydrogen this one has? It doesn't have any more hydrogens here. No more hydrogen on this carbon atom. So can you perform oxidations any further? No, because there is no hydrogen on the carbon atom. So you can put that in your note. No hydrogen left on the carbon atom that is pink colors. That's the one that's connected to oxygens. And also keep on tab on number of CO bond. How many CO bond we had in this molecule? One CO bond. So we got one CO bond. How many oxygen CO bond here? Two CO bond. But it doesn't have any more hydrogen, so it cannot perform any more oxidation. So keeping in the trend, let's see if you can perform this. Always look at the carbon atom connected to the oxygen and then figure out how many hydrogen it has. So this has 0 hydrogen on, so I should say 0 because otherwise it will confuse. 0 hydrogen on the carbon atom color coded with pink. So that's your alpha carbon atom for OH. So how many step oxidation it can do? So 0 step of oxidations. So which means this one will not perform any reactions, so no reactions. Okay, so as long as you pay attentions to only one thing, which is how many hydrogen attached to the carbon atom that is connected to the OH, okay, then your life would be a lot easier. So again, so this is the oxidation reaction. So you can perform the backward reactions. So that's going to be reductions. You can reduce a carboxylic acid. You can reduce an aldehyde to make an alcohol. Okay, so what happened when you oxidize secondary alcohol? Well, you make ketone. So that's the idea. Forget the reagent for now, and then we will go with the reagent later. So let's summarize what we just did. So we have primary alcohol can oxidize to aldehyde and then carboxylic acid. So this is oxidation. And then we got secondary alcohol that can oxidize to ketone and no more reactions. Then we got tertiary alcohol that can oxidize to nothing because there is no more hydrogen left. Okay, so now you couple of reagent that does two-step oxidation. So I'm gonna divide it this. So reagents that can perform, that can do two-step oxidations. So one such example is chromic acid, H2CrO4. Now you cannot make chromic acid on your own. You can see questions like this. Chromic acid can be made by a couple of different ways. You can make chromic acid by dissolving sodium dichromate in sulfuric acid and water. So if you see this in your questions, assume that this is chromic acid. There is another choices you can make. You can make chromium trioxide with acidic conditions, H3O plus, and with acetone. If you see this, this can also make chromic acid. So again, it can perform two-step oxidation. That does not mean it will. It depends upon the type of alcohol you have. Okay, so keep that in mind. So this is the only reagent that can perform two-step oxidations. And this one here, reagents that can perform. So these are a little bit milder reagent. A green chemistry perform one-step oxidations. Okay, so one is pyridinium chlorochromate with CH2Cl2. Another one could be which one? Desmartin periodinin. And again, this one is also going to be in dichloromethane solution. CH2Cl2 is DCM. And what else we got? Let's see. We also got Swan oxidations. So Swan oxidations will do, so it has oxalyl chloride, COCl, oxalyl chloride with dimethyl sulfoxide, oh dang it, DMSO, followed by, I'll rewrite this. So you are doing these reactions in DMSO solvents with oxalyl chloride, and then you add base in the second step, triethyl amine. And then also there is another one, hypochlorous acid, that's as well there. So again, let's recap. If you have these reagents, if the alcohol allows, it can perform one-step oxidations. If you have this reagent, if the alcohol allows, it can perform two-step oxidations. Okay, so keep that in mind. What's the term? If the alcohol allows. And how can we figure out if it allows or does not allow? So for example, this one here, this alcohol will not allow for any kind of oxidation reaction. So it doesn't matter what reagent you use, there will be no reactions. So let's do one quick questions. So for example, let's say this one here, OH. Now you look at the carbon atom that is connected to oxygens. So how many steps of oxidations you can do here? Because you have two hydrogens right there. So here, one hydrogen. So it can perform two-step oxidations. Now, this alcohol can perform two-step oxidation. That does not mean it will. It depends upon the reagent. So let's say I add chromic acid here. Okay, so let's say I add chromic acid. Then I will go over this. I still have one hydrogen left, and it can perform another step of oxidations. And bingo. So this is the answer you will write. Okay. Okay, so this is the answer you will write, because as soon as you make your aldehyde, it will immediately oxidize to this. Okay, so if you write this will be wrong. Okay, again, just because this alcohol can oxidize does not mean it will, because if you have to provide the right reagent. For example, let's say I provide PCC right here. PCC with dichloromethane, pyridinium chlorochromate with dichloromethane. This alcohol can oxidize twice, but the reagent is milder and it cannot oxidize twice, right? So for example, here you will end up with this, because the reagent cannot do it, even if the alcohol wants to. So the same is hold true. So if I would have used desmartin periodinin with dichloromethane, I would have got the same thing. I would have gotten the same thing if I would have used the Swan oxidation method. Okay, so the same thing. First thing you want to figure out what alcohol allows, and then next thing you want to figure out if the reagent does the job. Let's do one more example and then we call it quit on this video. This video is getting slightly longer. So let's say you have something like this here. All right, so how would you figure this one out? You always look at the carbon atom connected to oxygens and draw the hydrogens. How many hydrogen it has? One hydrogen. So this one has one hydrogens right there. So this means how many oxidations this alcohol will allow. How many step? So this alcohol will allow one step oxidations, no matter what the reagent is. Okay, so no matter what the reagent is. So that's critical. So if I use chromic acid, H2CrO4, I can only do one step oxidations because this is what my alcohol allows. And again, it doesn't matter what reagent I use. Desmartin periodinin with DCM or with Swan oxidation method. This alcohol only allows one step oxidations. So this was a secondary alcohol to begin with. So it will do one step because these reagents do only one step oxidation anyways, right? So in this type of problem, always begin with the type of alcohol. Figure out how many steps oxidation it can perform. Then look at the reagent and figure out whether the reagent can perform two-step or one-step. Okay, so that's how you solve this type of problems. All right, this video has gotten way too long. I'll stop here. If you're watching this video, if you can put a timestamp, like suggest a timestamp, I'll be happy to add the timestamp.